Hello everybody. A few minutes ago we were talking about rates of reaction and finding reaction constant. This is a preview of a lab that we'll be doing where we can experimentally work with that concept by reacting an aptly named crystal violet solution, or CV, with a strong base that generates strong base hydroxide ions, in this case sodium hydroxide. The reason why this reaction will be so effective for us in our study of these concepts is that crystal violet, of course, puts out a very strong purple color, but as it essentially disappears due to its loss of purpleness from its reaction, we can monitor that with a colorimeter, which is very similar to a spectrophotometer. Some of you may have used a spectrophotometer in my Chemistry 1 class when we were synthesizing aspirin, and thus trying to measure the amount of impure salicylic acid concentration by complexing our samples with a chemical that turned it into a purple, and thus viewing the increasing amount of purpleness of the solution as more impurities. In our case here, the crystal violet, which is modeled in this molecular structure, has a positively charged carbon atom in the center that will interact with the hydroxide, which is a negative from the sodium hydroxide, thus creating a crystal violet hydroxide. This causes, of course, the overall molecular structure and thus the electron configuration to change. We see that change in electron configuration as a gradual disappearance of the purple, ultimately to a clear solution overall. So, because of this, we can use spectrophotometry to determine quantitatively a rate of disappearance of our reactants, and thus an appearance or formation of our products. As we studied earlier, a rate of disappearance or a rate of change of the reactants is always a negative one, thus this is that negative. We can, of course, negate it and make it into a positive value. We're going to be looking at this reaction in respect to the crystal violet over time in this change. And this can give us a sense overall of a rate order equation by looking at whatever coefficient we drives CV against OH. We don't know, starting out, what this coefficient is. Is it a 0, is it a 1, or is it a 2? This, of course, is our orders of reaction. By looking at the data that we generate over time against the change in concentration, which is, of course, going to be a downward negative value, we can determine whether it is zeroth order action, first or second, with respect to a change in concentration of CV. If a change in concentration of CV has no effect on the overall rate of reaction and thus stays linear compared to, say, a first trial, we simply model that our rate is K, is our constant, it's our slope. On the other hand, if we have a doubling of our concentration causes a doubling of reaction, we can model this way, and we should see more or less this type of a change in the data once it has been graphed, and thus rate equals our constant times our change, our increased change in CV. However, if a doubling of CV causes a fourfold increase in our rate, or thus a fourfold decrease or increase in disappearance, so to speak, which is a sharper curve here, this is a second order reaction. This way, we can experimentally derive what kind of reaction we have with crystal violet reacting with sodium hydroxide to make crystal violet hydroxide. We can find its overall rate order with respect to CV, and we can derive the constant for this particular